So what we're going to go over today, guys, is hopefully going to seem familiar from Science 10. Okay, in Science 10 you went over work energy theorem, okay, and we're going to go over it again. I'm just going to add like a couple of small things to it, okay, but still in general the same idea. In Science 10, you learned that work is a change in energy, okay? That's what work is. So if we're just, right now, what's the definition of work? Work is a change in mechanical energy. Okay? Mechanical energy comes in two forms. What are they? Kinetic and potential. So when you do work, you are changing either the kinetic energy of an object, the potential energy of an object, or both. Okay? For mechanical energy, it is possible to change both at the same time. In Science 10, we never dealt with any problems where both changed. Okay? In Science 10, it was either work changed the potential energy, and if it did, the object got further away from the ground, or it changed the kinetic energy, which meant that the object either went faster or slower. Okay? Because kinetic energy has to do with speed, and potential energy has to do with height. And that's if we're dealing with gravitational potential energy. Obviously, there's also elastic potential energy, which we don't deal with in Unit 2. We save it for Unit 4, okay, when we're talking about elastic objects and things like that. Okay, so we need to understand that work is a change in energy, okay, and that we calculate a change in energy by going final mechanical minus initial mechanical energy. Okay, as we do with anything that's delta, right? Anything that's delta something, it's final minus initial. Okay, so if we're looking at that, okay, as our setup, and mechanical energy is both kinetic and potential energy, that's going to mean then that work equals our final kinetic energy plus our final potential energy minus our initial kinetic plus our initial potential. That formula is not on your formula sheet. Okay? What's on your formula sheet is that work is a change in energy, and that's it. Okay? We have to understand that change in energy means, okay, that these things are changing. Okay? Everybody okay with that? Okay. How do you do work? Applying force over, okay.
A specific period.
So I'm applying force right now for a few seconds. Am I doing any work? No. I didn't accomplish anything. Right? Did the wall move? Then I didn't accomplish anything. I didn't do any work. The wall did some work on me because my muscles contracted and got shorter. Okay, but other than that, no, I didn't do any work because I didn't change the mechanical energy of the wall. Right? Everyone okay with that? So it's not through time, it's over distance. Okay? If I do work, this is doing work. Okay? I applied a force through a distance. Okay? And for a little while at least, the chair was accelerating. Okay? That counts as work. Right? I actually have to cause a change in something for energy to change and thus for work to be done. So we learned last year that work happens when a force is exerted through a distance. Okay? So work is force times distance, but it's also a change in mechanical energy. So very often in this course, you'll see the work energy theorem written like that. Okay, where when you exert a force through a distance, you are going to change the energy of an object. Okay, now it looks a little bit busy when it's written that way. It doesn't mean that every time we do work, both kinds of energy change. Okay, but sometimes it does. In the end, it's not as complex as it looks. All right, so the things we got to get out of today, okay? What work is? Work's a change in energy. What's the relationship between force and work? Well, the more force I exert, the more work I can do. Okay? Or the greater the distance over which I do the work, the more work I can do. Okay? And then learn that depending on the situation, work and energy can be equal. Okay? If I start out with no mechanical energy and I do work, will my final mechanical energy equal the work I did? In a perfect physical world, yes. Okay? Because no work would be lost, or no energy would be lost in non-conservative forces. Okay? All right. So, strictly speaking, okay, work is done if a force is exerted through a distance. So force and displacement are essential elements of work, okay, as shown in this example here. If you ever had to push a stalled car. Okay, so the car is stalled, it's not moving, it has no mechanical energy. Right? You start pushing it, you're exerting a force through a distance, and you are causing not only its speed to change, but if the road's not perfectly flat, you would also be causing its potential energy to change. Agreed? Either way, there is evidence of a change in energy, and thus the work you have done. Now, what if that car stalls on a frictionless surface? It would be really hard to push because you wouldn't be able to get any grip. Yeah, exactly. It'd be hard to exert a force on it. So let's say that I'm standing outside of the frictionless surface and I throw a rope at it and I'm able to catch it with a hook or something. Right? Once I get it moving, or let's say it's already moving, do I need to do anything? No. Okay? It doesn't require any work because I wouldn't be changing its energy at all. It already is moving. Right? And it doesn't require any energy to keep it moving, because it's on a frictionless surface. Right? So strange situations like that can come up. Right? Now, do I always exert a force in exactly the same direction as the object moves? No. Not always, no. I mean, think of a tow truck. Right? The force a tow truck exerts on a car is angled, but the car moves forwards. Okay? So if we're talking about the change in energy of the car, it would actually only be the horizontal component of that force that's actually doing the work. Okay? So sometimes we have to bring in a little bit of vector stuff into this just to make sure that we are getting the force that's doing the work. Okay? All right, now the thing about work and energy. Work and energy are scalar quantities. Okay? They don't have an east or a right or a left, okay, or anything like that. If I do work, I simply change the energy of an object. That object can do whatever it wants with that energy. It doesn't have direction. Okay? And in fact, when we're talking about kinetic energy, it's speed, not velocity, that we use. Speed is scalar. Right? So something has energy simply because of its state. Okay? It's either in motion or above the ground or something like that. Okay? That energy does not have a direction. Now, strangely enough, even though work is a scalar quantity, it can be positive or negative. Does that seem contradictory?
Yeah.
Yeah, it does. Right? Because positive and negative is supposed to be a direction. Okay? Work can be positive or negative based on whether you're doing the work or if the work is being done to you. Okay? If the work is being done to you, you're gaining energy. Your change in energy will be positive because the energy is coming to you. The object doing the work, its work will be negative because it's giving that energy away. It now has less. Right? That sort of makes sense. So it's not about direction, it's about whether you gained the energy or lost it. Okay. So these girls here, when they push on this rock, are they doing any work? No. Okay? They're not changing the mechanical energy of the rock. They could push on that thing like that all day and all night and for the next few years probably. Okay? And it's not going to go anywhere. They're not going to change the energy of the rock. Thus, they're not going to do any work. Why would they get tired then?
With the rock being sharing work on them.
Yeah. the rock's going to do work on them, and they have to brace against that. Okay? When you exert a force on the rock, what does it do? It exerts a force back, and if I don't brace for that, I go flying back. So what I have to do is I have to brace, and I keep pushing. Well, when I push, my muscles contract. There's the distance over which that force is being exerted. That's work, okay? And it takes energy to brace myself against that work. Okay? So they would lose energy. It would be as heat to the surroundings, but it's still energy. Okay? All right, now, in a case like this is kind of the tow truck example I was talking about before. Sometimes we exert a force in one direction, but the work, or the displacement, is done in another direction. Okay? And so we have to keep that in mind and only use the part of the force that's actually doing work. Okay? And that, in this case, would only be the horizontal component of that force, which is why I would have to go F, this force here, times the cos of theta to get that side. That's the direction in which the box moves, therefore that's the direction in which the work was being done. Okay? So we actually changed the formula slightly in Physics 20 from Science 10 to look like this. F cos of theta times d. Okay? If I exert a force this way and the object moves that way, what's the angle between the force and the displacement? 0. What's the cos of 0? 0. No.
Or it's basically whatever the force was.
1. 1. The cos of 0 is 1. Okay? Therefore, F times 1 times d. So it doesn't do anything, right? The cos of theta becomes irrelevant because theta was 0. Okay? It only really matters when there is a theta. Okay? Here. Like here. All right. So that's where that cos of theta comes in. Sometimes, however, I put a force at an angle, and the box doesn't move at that angle, so I'm only doing work in one direction. Okay? And that would be here. Okay, so let's try this example, or look at this example right here, because we have the answer on the board already. Okay, so we have a 45 Newton force. So this force here is 45 Newtons. Okay, and they tell us that the angle is 50 degrees. And we're going to pull that thing 75 meters. Okay, so we would simply calculate the work by going work is F cos of theta, so that would be 45 Newtons times the cos of 50. Okay, times distance, times 75 meters. Here's how much work would be required to do that. 2.17 times 10 to the 3 joules. Okay, now remember, the units for work are joules because they're in Newton meter. Right, force times distance. A Newton meter is a joule. Now, if the luggage doesn't change its speed, and this is a level floor, did I change the energy of the luggage? No, I didn't. I moved it at a constant speed, which means I didn't change the kinetic energy. It wasn't uphill, so I didn't change the potential energy. I didn't do any work on the luggage. What did I do work on? Yeah, the ground. What's between the ground and the suitcase? Friction. Do I have to overcome that? Yeah, so really what that represents is that's how much work I did against the force of friction trying to resist me pulling the luggage along. Okay? I didn't change the energy of the luggage, but I did do work. Okay? That work just got turned into heat and sound and all the things that friction wastes energy on. Okay? But I didn't change the energy of the luggage. So it's possible for me to do work. It's just doing work kind of on the surroundings or against a non-conservative force, okay, like friction. Okay. So we're lifting weights, and we're doing the bench press. I've watched people, lots of people, do bench press. I've watched lots of people do bench press wrong. Okay? Like really, really wrong. They put way too much weight on the bar. They strain and grunt and they get the weight till their arms are straight. And then they go, yeah, and they just like drop it, okay? Are you getting much out of that workout? About half, okay? You want to do a workout properly, you lift slowly and you lower slowly. Why is that so much better for you and more work than just lifting it and dropping it? Right. Instead of you. Now you don't you want to make sure you catches on something, okay? Because otherwise, if you're going to do work on you, okay, and break your chest or something, okay, you don't want to do that. But if I lower it slowly, so if I raise it at a constant speed, okay, I don't change its kinetic energy at all. Am I still changing its mechanical energy?
Yes.
Because I'm changing its
Potential.
right. Now when I lower it, I also lower it at a constant velocity. I don't allow it to accelerate due to gravity. I lower it slowly. Okay? Am I still doing work? Yeah, because I am preventing it from accelerating. Okay? That means I'm not allowing the kinetic energy to change, which means I'm doing work against gravity, right? Or I'm absorbing the energy that the bar is losing. And because the bar has more energy here than it does here. Okay? But I have to do work in both directions. Okay? So, would it be pretty easy to calculate how much work would be required to lift the barbell? Yeah, okay? It's 710 newtons. That's the force of gravity. That's its weight. If I want to move it at a constant velocity, how much force do I have to exert? 710. Yeah, okay? I got to exert that much force if I want to move it at a constant velocity, because then the net force would be 0 and it would go up. Okay? So, and I would lift it 0.65 meters. So, work is force times distance. Okay? And I take my 710 newtons and I multiply that by 0.65 meters. Okay? What's the angle here between my force and my distance? 0. They're in the same direction. All right, so when I do that, I get 710 times 0.65. So that's 462 joules. Okay, when I lower it, how much work do I do? Okay, let's look at this from the barbell's point of view. When I lifted this, is that how much energy the barbell gains? Okay, from the barbell's point of view, when I lower it, that number is going to change to negative 462 joules. Why? It's doing work on me, and the angle is different. I'm exerting a force upwards, but the barbell is moving downwards. How many degrees is that? 180. What's the cos of 180? -1. F cos of theta times d. When theta is 180, this becomes -1. Force times -1 times d gives me the same number, but now it's negative because the barbell is now losing energy. It's doing work on me. Okay? It's changing my shape. Right? My muscles are going to change shape as I lower the barbell back down. Okay? Everybody okay with that idea? All right. Very rarely do we ever do any stuff with this cos of theta thing. It's very, very rare that it comes in. We just have to understand that it's there. Okay? Okay, so to change the potential energy of an object requires how much net force? With the barbell? 0. Right? As long as I exert enough force to overcome the object's starts with W. Weight. Okay? I can change the potential energy. Okay? It doesn't require me to change its speed, I just move it at a constant speed. Okay? So if there's a net force, what happens to the object? It accelerates. If it accelerates, that's a change in speed. And if I change the speed, what kind of energy do I change? Kinetic. So, if I have a situation where there's a net force, I'm going to accelerate the object. And its kinetic energy will change. Okay? But it's possible to do work even if there's no net force. Okay? If there's no net force, it just means it's traveling at a constant velocity. I could still be changing the object's potential energy. If there's a net force, I could be changing both. Okay? But it's possible to do work even if there's no net force. Okay? It's about the applied force. Okay? That's what does work. All right. Okay, so remember that in order to do work, you have to have energy. Okay? We're going to find that out tomorrow when we're all have to shovel snow again. Okay? You're supposed to get a lot like over the next couple of days. Okay? Your parents wake you up and they go shovel the driveway. You're like, I don't have any energy. That's what my kid will say. And I'll say, yeah, you do. You just talked to me. Get up and shovel the driveway. Okay? Because I mean. So, you have to have energy to do work. Okay? You can't transfer what you don't have. And remember that work is a transfer or a change in mechanical energy. You can't give what you don't have. It's not like a credit card, okay, where you can spend what you don't have. Okay? Energy works. If you don't have it, you can't give it away. All right. So, things to remember. Work's a change in energy, and these formulas that we learned last year. Kinetic and potential energy. Right? So kinetic energy is dependent on two things: the mass of the object and the speed of the object squared. Potential energy is dependent on the mass of the object, the acceleration due to gravity, and the height, or the change in height. Now, we just said that work is force times distance. If I do work that changes the potential energy of an object, I use this formula, yes? Okay. What does m times g calculate?
Weight.
Weight, which is the force of? And is height a vertical distance? So is this formula force times distance? It is. Okay? So as long as you exert a force equal to the object's weight over a distance, you will change its potential energy, because potential energy's formula is force times distance. It's just the force of gravity times distance. That's, again, why you don't need a net force to do work against, or to change the potential energy. Okay? But you do need a net force to accelerate something, okay, and change its kinetic energy. All right, now, in this formula, speed is squared. So if I change the speed of an object, or I go faster, what does that mean for the amount of mechanical energy I have? It goes up, but how does it go up? Linearly or exponentially? Exponentially. If you double your speed, you have 4 times as much mechanical energy. This is kinetic energy. Right? That's something to keep in mind when you're driving. Okay? The faster you go, you have exponentially more energy. Now, real life physics application here. If I have kinetic energy and I want to stop, so let's say I'm moving at 10 meters per second and I want to stop, what has to be done? Work. I have to turn that kinetic energy into something else. In a car, whose job is that? It's the job, the brakes. Okay, what do the brakes do with your mechanical energy? What do they turn it into? Heat and sound, okay, maybe even light a little bit. Okay, if you've ever watched like nighttime racing, okay, try it sometime. The brake rotors will glow cherry red when they're braking. Okay, they actually get that hot. Okay, they turn into heat and they actually emit visible red light. Okay, So if I want to slow down or stop, I have to change my kinetic energy, which means I have to use the brakes, the force of the brakes, over a distance. Okay? Now we know that work's a change in energy, so that's going to mean force times distance equals if you were in my science 10 class, I gave you this lecture last year, so it's a good refresher. Okay? All right. This would be how I would calculate how much work would be required to stop me. Agreed? What do I want my final mechanical energy to be, or my final kinetic energy to be? Right. So really then, the work I have to do is equal to 1/2 mvi squared. It's equal to my initial kinetic energy. Okay. Now, my car can only exert so much braking force when I pile on the brakes. Okay, if I slam on the brakes as hard as I can, I max out the braking force my car can exert. Okay, so my initial speed and the braking force are already predetermined. But the faster I'm going, what happens to this number? It gets bigger. It gets bigger exponentially. So if I'm going 30 kilometers an hour, it's going to take me X amount of distance to stop. If I'm going 60 kilometers an hour, it's going to take me 4X to stop. I double my speed, but I quadruple my stopping distance. Okay, so mathematically here, if I want to calculate stopping distance, let's just say that my car can exert 2,500 newtons worth of braking force. I have no idea what the normal braking force of the car is. I'm just picking. Yeah, I'll make it bigger. Let's say my car can exert 8,000 newtons. Let's say it's really sticky. Okay, 8,000 newtons worth of braking force. And let's say that I'm traveling at the speed limit. I'm going through a playground zone, so that's 30 kilometers per hour. Okay, I got to convert that to meters per second. Okay, 8.3. So I'm moving at 8.3 meters per second. Now I want to calculate how far I will travel before I stop. Oh, and the mass of my car is 2,000 kilograms. Okay, so D is going to equal 1/2 times the mass times my speed squared in meters per second divided by my braking force. Right. So when I plug in these numbers, that's 1/2 times 2,000 kilograms times 8.6 squared divided by 8,000 newtons. Sorry, 8.3. It's not supposed to be 8. It's supposed to be 8.3 squared. Okay. Divide that by 8,000. All right, so I will travel 8.7 meters, 8.68 meters before I stop. That's a long way. That's like almost the length of this, well, not quite the length of this room, but pretty close. Okay, is that a long way? Especially if a kid runs up in the street. Especially if they're less than 8.68 meters from you when they do it. But you're going 30 kilometers an hour. So you're going to slow quickly. Okay, and remember that for every meter per second you slow, you're going to have exponentially less energy. Right? That's why there's a slow speed limit to a playground zone or a school zone. Now, if I was an idiot and I was going 60 kilometers an hour through this playground zone, which I would never do, but I've seen people do, okay, this is how this equation changes. Okay? So the distance is now 1/2 times the mass of the car times now twice the speed I was going at before. Okay, so now I'm going 60. That's 16.67 meters per second. Okay? And my brakes can still only exert 8,000 newtons worth of force. 8.5 times 2,000 times that number there squared divided by 8,000. So I go from 8.7 meters to 34.7 meters. Is that a lot? Yeah. And for your sake, it better not be my kid. Okay? Think about this. Exponentially more energy means exponential change in stopping distance. It doesn't take much before your stopping distance is really, really big. Okay? And remember, I said this was going to be how many times bigger than the first one? 4 times. How do I get out of there?
Second load.
Four times, right? I only doubled the speed. I only doubled the speed, but I have 4 times as much energy, and thus I require 4 times as far to stop. Okay? And this also has a similar relationship with mass. Okay? Now, mass isn't exponential. Mass is linear. But if I'm driving a Honda Civic versus, like a big truck, the big truck is going to take further to stop because it's bigger. Okay, it has greater mass. Now, it should also have greater friction because of its greater mass, but it's bigger. It's going to have more energy. It's going to take longer for it to stop in terms of distance. Okay, so obviously, very few people are, this stupid. Okay, very few people would go 60 through a playground zone. There are some, okay? Like that lady that went through the Westmount school zone and nearly ran the enforcement officer down. I kid you not. On the phone, okay? And the municipal enforcement guy is there doing a speed trap, and he had to dive out of the way to avoid being struck by a distracted driver who was going double the speed limit through a playground zone at 3:20 in the afternoon on a school day. See, there's a special kind of stupid out there. Okay? Yeah.
That's a lot of charges too.
I hope
bet
she
you
lost her
made a
license.
million.
Anyone that would make that decision does not deserve to drive. You should take public transit for the rest of your life if you are making those kinds of decisions. You may. Okay, so obviously we wouldn't go this fast, but do we sometimes convince ourselves that it's okay to go 10 over?
Yes.
Yeah, we tell ourselves that all the time. It's only 10 over. It's not a big deal. It's only 10 over. I won't even get pulled over for that. Okay, well, remember, it's exponential. So instead of going 30, now I'm going 40. Whoop. Okay, so I'm going 11.1 meters per second instead of 8.3. Okay, well, so that's 0.5 times 2,000 times okay, when I was going 30, it was 8.7. I'm only going 10 kilometers an hour faster, and it's now 15.4. Almost double. I only increased my speed by 25%, but I almost doubled my stopping distance because kinetic energy, and thus stopping distance, is exponentially related to how fast you're going. Have I said that enough times for that to sink in? Okay. It's really something you need to know. I don't know why they don't teach this in driver's ed. They just say the faster you go, the further it takes to stop. Yes, but it's exponential. That's a lot different than it's just further. Okay? It's exponentially further. Okay? That's why speed fines double through a construction zone. Okay? It's going to take you a lot further to stop because of your extra kinetic energy. Your brakes, their job is to do work, to turn that kinetic energy into something else. But they can only do so much. Okay? If you have lots of energy, they have to do a lot of work, and it takes them a long distance to do it.
Cars also have anti-lock brakes, which means they climb really fast instead of just holding down, which means now it's only doing work like half the time.
But it's also maximizing your static friction instead of kinetic. Because back in the day, you piled on the brakes and you slid. You skidded to a stop, which on dry pavement is actually pretty fast. But, yeah, under other conditions, having the wheels locked up is bad. And if the wheels are locked up, what can you also not do? Steer. Okay? So the advantage of anti-lock brakes is that kid ran out in the street and you're trying to stop as fast as you can, but you could swerve. Okay? If your brakes are locked up, you can't swerve. Okay? So that's the advantage. They typically, under most conditions, also stop faster, but they also allow you to steer while stopping, okay? Which wasn't the case, 30 years ago. Okay. Is that making sense? Okay. So, really important to recognize, work energy theorem has lots of real life applications, this being one of them. In a playground zone, or a school zone, or a construction zone, or anywhere for that matter, go the speed limit. Okay? They're there for a reason. Okay? And it's not to be inconvenient, it's safety. Okay? Because guys, that 40 kilometers an hour, right? That 10 kilometers an hour almost doubles your stopping distance. How much time does it save you? Maybe. Depends whether you hit the red light. You could be stuck behind the same red light. How many times have you been passed by someone driving like an idiot, only to end up right behind them at the next stoplight anyway?
Yeah.
Like, what did they gain? All that craziness, nearly risking accidents for 10 feet. Okay? They got 10 feet ahead in the end. So you got to think about stuff like that. But here's the real kicker. Let's say this playground zone, because most playground zones are somewhere around 200 meters in length. Okay, like the one over in Darcy, that new one there. Okay, it's about 200 meters in length. T equals D over V. So 200 over 8.3. Here's how long it takes you to go through that at the speed limit. Okay, it takes you 24 seconds. It takes you 18 seconds if you go 40. Saves you 6 seconds. Boy, I keep pressing buttons. Okay, saves you 6 seconds. If you're so late that those 6 seconds are important, get up earlier. Okay, be more organized. Because those 6 seconds could be the difference between me having dinner with my son or planning his funeral. Those 6 seconds are very important to me. Yeah? Now, that doesn't mean you can show up late and say, Coderre, I drove 30 because you told me I wasn't allowed to speed and now I'm late. No, you're late because you didn't get up early enough. Okay? You can't, because I had someone try that once. Okay? None of that logic doesn't fit. Okay? It doesn't work. All right? But it's important. Okay? It's really important. Think about that the next time you're going a little too fast. And then don't go a little too fast. Okay? All right. So, no, we don't need to do that one. Okay, I would like you guys to try question 1 and question 2. Simple work problems like this. They're just like work is F cos of theta times D. They're simple ones. So we'll start with those, and then we'll go to some true work energy theorem questions. Okay. So, you pull a sled along a horizontal surface by applying a force of 620 newtons at 42 degrees above the horizontal. So, here's the sled, okay? This is horizontal, but you're pulling this way with 620 newtons, 42 degrees. So, the sled's not going that way. The sled is going this way. So, if I want to calculate the work, okay, then I just have to go F cos of theta times D. So I'll take my 620 times the cos of 42 times 160 liters. Okay? And that will get me the amount of work that I do in that particular situation. So 7.4 times 10 to the 4 joules. Okay. All right, how are we doing on number 2? We can go over number 2? Yes? Okay, so on number 2, they are wanting us to calculate the force on this one, right? So they tell us the work. It's 9,600 joules, okay? And they tell us the distance, 25 meters, and they tell us the angle, 30 degrees. So work equals F cos of theta times d. So if I want to get F, I just divide both sides by the cos of theta times d. That'll leave me with force, okay? And so then I go 9,600 divided by the cos of 30 degrees times 25 meters. That all needs to be in brackets on the bottom for this to come out right. So 9,600, okay, divided by the cos of 30 times 25. All right, so 443 newtons would be our force there, and it would probably be forward or something like that, because force is a vector quantity, and so that should have a vector form. Okay, questions there? All right, I want you to copy this one down, because this is a work energy theorem question, and it involves both potential and kinetic energy changing. Okay, because back in Science 10, you only had to do questions where one or the other changed. Now you're going to have to do questions where both change. Okay, so I want you to copy this one down, and then we'll walk through it. All right, so for a work energy theorem question, there's actually 2 ways to solve them. Okay, using work energy theorem, which is much faster and more efficient, or as a Newton's second law problem with a work is force times distance calculation at the end, which takes much, much longer and has far more opportunities to make a mistake. Both ways are equally valid and will arrive at the same answer. Okay, but I see people oftentimes forget that they can use work energy theorem. They resort to Newton's second law because they're familiar with it, and it literally takes them 3 or 4 times as long to do the same question. Okay, so I'm going to show you how to solve this first off, what I would consider to be the better way. Okay, and that's using work energy theorem. Okay, so according to work energy theorem, work is a change in mechanical energy, right? That means taking our final mechanical energy and subtracting our initial mechanical energy. Now in Science 10, we learned that mechanical energy is an object's kinetic plus an object's potential energy. Okay, that's how we calculate mechanical energy. So what I want to do in the end here is find the object's final mechanical, initial mechanical, and subtract the 2. Okay? Is finding those 2 types of energy fairly straightforward? Yeah, I just plug in the numbers into the formulas, 1/2 mv squared and m times g times h. Okay? And then I just have to subtract. So there's really not much to do that way. Right? So let's write down all the givens that we have. Okay? I know that my initial speed is 1.00 meters per second. What's my initial height, according to this question? 0, because I'm at the bottom of the ring. Okay, how much potential energy then do I have at the start?
0.
Right, I don't have any. Okay, so one thing just got easier. I don't have any potential energy, so I can not bother spending time doing that part. Okay? All right, from the final perspective, my final height is 0.850 meters, and the final speed is 4 meters per second. Is work being done here? Definitely. Not only is the object going to be higher, indicating a change in potential energy, it's also being accelerated up the ramp. It's moving faster at the top than it is at the bottom. So lots of work is being done. Okay? All right, so if I want to calculate the work, and I'm going to use work energy theorem, what I have to do is keep expanding this formula out. All right, so I'm going to have work equals, okay, my final kinetic plus my final potential, okay, minus my initial kinetic plus my initial potential, which I already know is 0. Right? I don't have any potential energy at the beginning of this question because I'm at the bottom of the ramp where I have no height. Okay? So I can take that out. All right, I'm going to expand it a little bit further. Now I'm going to say this. There's my final kinetic energy, 1/2 times the mass times the final speed squared, plus my final potential energy, m times g times my final height, okay, minus my initial kinetic energy, 1/2 times mass times the initial speed squared. Okay, do I have to do any manipulating? Nope, I just have to plug in the numbers. Okay, this is going to calculate work directly. All right, so 1/2 times, what was the mass of this thing? 1.2 kilograms, all right, times 1.2 times 4 squared, my final speed, plus 1.2 times 9.81 times 0.850, my final height, minus 1/2 times 1.2 times 1 squared. Because that was my speed at the bottom, 1 meter per second. It's a lot of numbers, yes, but at least it's not a lot of manipulating. All right, 19 joules. So that's how much work would be required to accelerate this block up the ramp to 4 meters per second, 0.850 meters higher than the bottom of the ramp. Okay.
Are we going to get a formula like this provided?
I said that already.
Oh, my bad.
The only formula that's on the formula sheet is work is a change in energy.
Okay.
You have to understand that that means, like, you have this formula, it's on your formula sheet.
Okay.
MGH is on your formula sheet. This is something you have to put together. Because the only thing that's true all the time is that work is a change in mechanical energy. You might not have potential energy. You might not have kinetic energy in one example. So we have to keep giving you formulas for every situation.
Yeah.
Yeah, so you have to decide what's my situation in order to do this right. Okay? All right, does everyone follow what we did there? Okay, so that, believe it or not, that's the short way. I mean, we only really did one calculation here. Okay, we had this formula and we plugged our numbers in and solved it. That was one operation, really. If I want to solve this as a Newton's second law problem, I have a lot more work to do. Okay? First off, I would have to know this angle. Like right now, I can't even solve this problem with Newton's second law because I don't know the angle. Okay? To solve this with Newton's second law, I not only need the angle, I need the length of the ramp because I've got to calculate the acceleration so that I can calculate the net force, so I can calculate Fg, so I can calculate F parallel, so I can multiply them by force times distance. Like I'm already up to 5 things. Okay? Instead of one operation, 5. And every time there's a chance to do something wrong. So we definitely want to try and solve these using work energy theorem because they're simpler. Okay? They're shorter to do it that way. Okay, what do we got here? Not too bad. All right, let's take like a 3-minute break here, and then we're going to give 1 and 2 a try here. want you guys to have a look at 1 and 2 here. Context is important. It helps you to kind of visualize what's happening here. In number 1, okay, has anyone ever like done any rappelling? Okay, where you lean back over the side of a cliff and then you kind of push off and the rope goes through your carabiner and you basically hop down the mountain, right? If you've never done that, it's fun. But it also, you have to be careful because as you're rappelling down, what's slowing you? Friction. Friction between the rope and your aluminum carabiner. So what do you suppose happens to the carabiner and the rope? Yeah, they get really hot. Like you can easily burn your arm on the metal of the carabiner if you're not careful when you get to the bottom. Where is that heat coming from? Okay, friction, but what is it getting rid of? Like when you're at the top of the mountain, you have a lot of this, but you don't have it at the bottom. Right. Okay, is there work being done here? All right, that's what you've got to figure out. Okay, work's being done. Okay, you're changing energy. You don't have the same amount of energy at the top as you have at the bottom. It's work energy theorem. Okay, see if you can figure it out from there. Right, and number 2, similar. Okay, but this one has to do with that idea that a net force causes a change in velocity or a change in kinetic energy, but this thing's also being lifted. So there's 2 ways to calculate work. Force times distance, or F cos of theta times distance, and change in energy. I can't use force times distance for number 1 because I don't know the force of friction, and that's what's doing the work. Okay? So what I have to do then is say, all right, work is going to be the change in mechanical energy over the course of the rappelling. Okay? So what I know here is the height, and I know the mass, and I know the final speed. What do you suppose the initial speed is?
0.
Right. Okay, so can I do this then? I can say my initial speed is 0 meters per second. My final speed is 5.0 meters per second. My initial height is 25 meters, right? It's 25.
Yes.
And what's my final height?
0.
Okay. So can I expand this formula out so that I have final mechanical and initial mechanical energy output? Okay, it'll look something like this. Work equals my final kinetic plus my final potential minus my initial kinetic plus my initial potential. Are any of those 0? Which ones?
Final potential and your initial kinetic.
Okay, did this question just get a lot simpler? Yeah. Okay, so now I can simply say 1/2 mvf squared, which represents my final kinetic energy, or sorry, final mechanical energy and final kinetic energy, okay, minus my initial mechanical energy, which just happens to all be potential. Okay, this is the change in energy. I only had potential at the beginning, I only have kinetic at the end. Whatever the difference is how much work was done on the rope as I fell, or repelled. Hopefully repelled, not fell. Because if this is fell, energy is conserved, and no work is done, except on me by the rocks at the bottom. Okay, that's bad. So, yeah, in this case, we were slowing ourselves, and we're calculating essentially how much heat friction is going to build, okay, as the rope goes through the carabiner. So we will have then 1/2 times 72 times 5 squared minus 72 times 9.81 times 25. Okay, I get a negative number. Is that okay?
Yes.
Yeah. The climber has less energy at the bottom than they do at the top, thankfully. Okay, because if you have the same amount of energy as you do at the top, you're going very fast. Okay, and that's bad. So the rope essentially slows the person or takes away from them 1.68 times 10 to the 4 joules worth of energy. okay, or does 1.68 times 10 to the 4 joules worth of work in slowing the repeller down. Okay, everyone all right with that idea? Okay, all we did was calculate how much did the energy change between the top of the cliff and the bottom of the cliff. That energy change is the work that was done by the rope, okay, in slowing the climber as they went down. Right, and it's okay to get a negative number because that represents energy lost by the climber and gained by the rope, okay, or the surroundings, whichever. Following? How are we doing on number 2? Haven't started? Okay, so I'll give you a few more minutes on number 2 then. Okay, let's have a look at 2. So they tell me the force and they tell me the height. What can I calculate with those two things? Nope. Can I calculate the work? I mean, height is the vertical distance, right? So if I do that, 150 times 5, I should get 750, right? Okay, so I get 750 joules right off the bat. That's an easy calculation because I had force and I had distance. All right. Part B says, what's the change in gravitational potential energy? It just says it was lifted. It doesn't say lifted at a constant velocity. Okay, we can't just assume that the only thing that changed here was the potential. There could be something else. So, can I calculate the change in potential energy? That would be like this. Could I do that? What's my initial height? 0. It says it was lifted. We have to assume that's from the ground. Okay, because I don't know where else to lift stuff from. Okay, so that means that my initial is 0. And then if I want to calculate the change in gravitational potential energy, I just have to take 9 kilograms times 9.81 times 5 meters, because that's the height it was lifted to. So 9 times 9.81 times 5. All right, 441.45. Joules. Okay. So I did 750 joules worth of work, but only 441 of it was necessary to change the potential energy. What did the rest do?
Would it be like released in heat?
No. It changed the kinetic, yeah. So this object, when it was lifted, accelerated upwards. Okay, it didn't move upwards at a constant velocity. There's energy left over. There's work left over. Okay, the rest of that energy change has to be kinetic. That's how you solve C. We don't have any speeds here. I can't go 1/2 mv squared, but I can say that the change in mechanical energy is the change in potential, okay, plus the change in kinetic. That would be true, right? I know this one is 750 minus 441.5 should leave me with the change in kinetic energy. And so if I do that, I should get what's left, which is 309 joules. Okay. So since there was a change in kinetic energy, that means the object must have accelerated upwards. Everyone okay with that? Okay. Now, just want to quickly look over something here, okay, in number 3. It says, draw a free body diagram and calculate the net force acting on the mass. Okay, this is essentially an elevator, yes? All right, so we were using 150 newtons up. The thing only has a mass of 9 kilograms. Okay, so the force of gravity that was down is only 88.29. So can I get my net force? Okay, so if I get my net force, that's my net force. Okay, how far did that net force act over? 5 meters. Was that my kinetic energy? Okay, earlier in class I said, if you have a net force, the object accelerates. Therefore, when a net force is present, there'll be a change in kinetic energy. because net force times distance will calculate your change in kinetic energy, because you don't have to accelerate something to change its potential energy. So, come full circle. We'll talk more about that tomorrow. Okay? You will have a quiz tomorrow. It'll be Newton's third law tomorrow. Okay? I will post that later on today.